Okay, we're going to start with a quotation from Kepler, because Kepler has an intimate connection with this instrument. And this is from Astronomia Nova. It's from chapter 19, for those who know the book. And for those who don't, what has happened so far is that he has constructed a model for the motion of Mars, which is, as he says, it's constructed in imitation of the ancients. What does he mean by that? It's that he uses only circles, and he insists that there be regular circular motion around some point which lies on the line of apsides. And he's come up with a pretty good theory. And I won't go into he's actually come up with a couple of them, and I won't go into the details, but he finds that his best fit theory results in an error of 8 arc minutes. And he talks about the importance of that in this chapter 19. He says, and from this difference of 8 minutes, so small as it is, the reason is clear why Ptolemy, when he made use of bisection, bisection means he puts the eccentricity of the eccentric exactly halfway between the point of the equant and the point of the observer. When he made use of the bisection, Ptolemy was satisfied with a fixed equalizing point. For if the eccentricity of the equant, whose magnitude the very large equations in the middle longitudes fix indubitably, be bisected, you see that the very greatest error from the observations reaches 8 minutes. And this in Mars, which has the greatest eccentricity of all the planets. Now, Ptolemy professes not to go below 10 minutes, or the 6th part of a degree, in his observations. That is, his observations are to the nearest 1/6 of a degree. The uncertainty, or as they say, the latitude of the observations, therefore exceeds the error in this Ptolemaic computation. Since the divine benevolence has vouchsafed us Tycho Brahe, a most diligent observer, from whose observations the 8-minute error of this Ptolemaic computation is shown in Mars, it is fitting that we, with thankful mind, both acknowledge and honor this favor of God. For it is in this that we shall carry on to find at length the true form of the celestial motions, supported as we are by these proofs, showing our suppositions to be fallacious. What suppositions? It's the ones he started with: circular orbits, regular circular motion around a point. In what follows, I shall myself, to the best of my ability, lead the way for others on this road. For if I had thought I could ignore 8 minutes of longitude, that is the 8-minute discrepancy, in bisecting the eccentricity, I would already have made enough of a correction in the hypothesis found previously. Now, because they could not be ignored, these 8 minutes alone will have led the way to the reformation of all of astronomy and have become the material for a great part of the present work. Okay, so where did the 8 minutes, what was it that showed up the 8 minutes error? He said it was the observations of Brahe. Well, the question is really not just what were the observations. He gives credit to Brahe for being a superb observer, but what were the instruments? What was the technology? Nobody has been able to look at the technology that Brahe used for at least 300 years. So we don't know. And this is where the Armillary comes in. When Kepler is saying something is important, we had better listen. So the question is, can we not just recreate Brahe, That's impossible. And Brahe, in fact, didn't do all his observations. He had people who had superb eyesight. But Brahe got within about 1 or 2 arc minutes. How did he do it? And the question is, can we recreate Ptolemy's technology, Tycho Brahe's technology, so that we can see exactly what the instrument itself was capable of? And at that point, we switched to St. John's in 2004. The question arose among the class of 2000, for the graduating class that year, well, what should we give the college as our graduation gift? Mark Rollins happened to be there at the meeting, and he quietly suggested that we might fund the construction of an armillary sphere. And people were saying, well, what's that? And Mark, knowing the history of astronomy, explained the importance of Brahe's armillary. And everybody said, yeah, that would be such a Johnny project to recreate a 400-year-old astronomical instrument that we could actually use. We could see what they were looking at. In the lab, for example, we don't just read the works of the writings of Faraday. We actually go into the lab and we try to do what it was that Faraday was doing and see what as much as we can, what he was seeing. So let's see if we can do the same thing with Brahe and Kepler. So the response was extraordinary, and the leadership that stepped up to run this campaign of raising the funds to get this armillary was also extraordinary. This is the result. It is the world's only functioning replica, as far as we know, of any of Tycho Brahe's instruments. We now do the Johnny thing of, here we have this thing. Nobody's ever seen it before. Nobody knows how to use it. So this is our territory. We are the ones who are specialists in doing things that nobody nowadays understands how to do. So we're going to be exploring this in the tutorials, and we've only just begun to see how to use it. So what I'm going to do in the rest of this presentation is to first of all explain the parts of the instrument, what they do, and then we're going to look at the some of the details, some of the things that are special about this that let Brahe produce observations that were 10 times as accurate as anything that had been done before. And then we will see how that works on an actual observation of a celestial body, namely the moon. This is an introduction to the armillary and all of its circles. And first I want to do the overview of the instrument, and then we'll look at the parts. The instrument is set on a level base. This is all carefully leveled, so it's aligned with the horizon, and it's also set up so that this whole frame of the instrument is vertical. That's done with a plumb bob hung from the top, and it hangs right in the middle of this hole here. And if the chord is tangent there and up there, then you've got your vertical line. You also have to align it north-south, which is a little bit tricky because you can't do it with a compass because the compass doesn't point true north. So there's various tricks, and I'm not going to go into them. But we've oriented this north-south along this side. The next part in going inward is the meridian circle or meridian ring. This is, it starts down at the bottom here, it goes all the way around, over the top, down the other side. So it's the biggest ring in the whole instrument. And you can see that it is calibrated up to Well, it starts at 0 here, and it's going in both directions up to 180 degrees at the other end. Now, why is not 0 at the bottom? It's because this is the ring where you set the latitude of the location of this instrument. So we go to a map, we find our exact latitude on the map, and then at this pointer, we set the latitude. And we can set that very accurately because it's got Tycho Brahe's 1 minute degree divisions. And why are we doing that? We're doing that because the whole thing turns on an axis. Here is the axis. This axis we want to point exactly towards the point of rotation of the whole heavens, so that every motion of the armillary corresponds to a motion of the heavens. And if you come around to this side, you can see, you would be able to see, if it were night, you would see that this axis is pointing towards the North Star, almost exactly. The next ring is the equatorial ring, so-called because it's parallel to the equator. So let's look into that. The equatorial ring is this one that I've got my hand on right here. And you'll see that because it is mounted perpendicular to the axis here, as it rotates, it stays in one plane. It's 90 degrees away from the direction of the axis, the orientation of that plane. Well, putting it the other way around, the axis is perpendicular to the plane of the equatorial ring. And also, the equatorial ring is, because of its orientation perpendicular to the axis, it's parallel to the equator in the heavens. So that as it rotates along, it can be made to rotate along with the heavens, or it can be adjusted so as to be directed towards any point in the heavens. How can a circle be directed? The circle as a whole just stays perpendicular, but it has calibrations all the way around, which you won't be able to see on the video so easily, but they correspond to positions in relation to the equinoxes and solstices. The final circle, the innermost circle that I got my hand on, is the declination circle. And it's so called because it measures the angles above and below the equator. You can see that this is 10 degrees, 20 degrees, 30 degrees. This would be north of the equator. 0 is right on the equator, and then there are south declinations this way. And together with the equatorial ring, it can provide a complete coordinate system for the positions of any celestial body. That is, the equatorial ring tells you where the body is around the circle, and the declination ring tells you how far north or south that is of that particular circle. Now, you may have been wondering about this odd-looking plastic thing, hula hoop sort of thing, put on here. This instrument is designed to be a functioning replica of Tycho Brahe's observational instrument, his armillary, and specifically it's his second armillary. And because it's an observational instrument, it doesn't need any more complications than the complete coordinate system that I mentioned when we were talking about the declination circle. But if you wanted to give a model of where things are, give you a picture of that, you'll want to have a mid-zodiac circle. That's what this is. This is the oblique circle that is going through the equinox points. at the two ends, and then it tilts up in declination and down in declination at the two solstices. So specifically, the motion of the planets stays always close to this circle. This is the spring equinox, and they all are moving this way around this circle. When it's about 90 degrees around from the spring equinox, it gets to the summer solstice, which is tilted farthest north, and then autumn equinox around here, and then winter solstice down here. The tilt of it is just about 23.5 degrees, and I've got it running right through the 23.5 degree mark here. So it should correspond very closely. Let me just point to that. It should correspond quite closely to the position of the planets in the sky. Now, we happen to have two of what Ptolemy would call the planets, namely the sun and the moon. And what I have done is I have set up pieces of cardboard on the circle corresponding to where the moon is right now and where the sun is right now. Now, this is in relation to this instrument, but because the instrument turns, we can align these cardboard replicas of the planets with their real counterparts in the sky. So I'm going to rotate this around, and if you come around and look at not at the armillary, but at the shadow on the ground. Over here, do you see the shadow? This is our sun. So the rays of the sun are coming from the sun itself, passing over that little cardboard thing and hitting the ground. This little point marks the geometrical middle of the entire instrument. So if I have gotten the sun in the right place, as I turn this, the sun will go right through the middle. And there it is. Very slightly off, but very close to the middle of the instrument. Okay, so now we have the cardboard sun aligned, so that if you drew a line from the middle of the armillary through the cardboard sun, it would pass through the real sun. So we've got that side of it aligned. Now, the challenge is, if you draw a line from the middle of the instrument through the cardboard moon up there, will you find the real moon? If the positions that I've marked with the cardboard correspond to the real positions in the heavens, they ought to line up. So let's test it. Okay, so here we are looking up past the cardboard moon, and if you look up just to the left of the cardboard moon, you can see a little bright thing in the sky. That's the actual moon. And we're almost perfectly aligned with the center of the instrument. I'm going to move it over so as to get it lined up perfectly. There we are right in the middle. Of course, since it's lined up, we can't see the actual moon because it's back behind the axle and it's back behind the cardboard moon. So let me back it back out again. And there we are looking at the three in line with each other. Now we're going to move on to some of the details of the instrument in preparation to doing an actual observation. And here we have one of Brahe's sights. He was very proud of this invention, and I'm going to explain the pieces of it as we go along. First of all, the slits. He has these two slits, and the upper. These two slits we're not going to worry about right now. This slit here and this slit here are, first of all, very narrow, and second of all, they're spaced at a precise distance, and their spacing is exactly the same as the diameter of this cylinder that you see up there. The idea is you use the upper sight to sight along one side of the cylinder and the lower sight to sight along the lower side of the cylinder. And if you line those up on the same star, then you are confident that you've got your sight perfectly lined up. So I'm going to try to line it up on something in a minute. But first, let's have a look at the scale, which was actually devised by Levi ben Gerson in the 13th century. But it was not really very well known until somebody happened to tell Brahe about it early in his career, and Brahe enthusiastically adopted it and adapted it to a curved scale. And here we are looking at the indicator, which is set at slightly more than 20 degrees. You see the 20 up here, and it's divided into, here's the 20 degree mark, here's the 20.5 or 20 degree 30 minute mark. Each of the small divisions here is 10 arc minutes, and you'll notice that in between, and I'm going to try to get this to where we get a good reflection. In between, we have these little diagonal dots that run zigzag along here. And what you do is you count. Now we are at, let me check for a moment. We are at 20 degrees, and down here, you can see, if I can get my pointer out, 30 minutes and a little extra. So you count the dots along the edge here, and I don't know how clearly it is visible, but we count about maybe 7 or 8 dots. So it's 20 degrees and 38 minutes. And this is the thing that enabled Brahe to measure individual minutes instead of getting down just to 1/6 of a degree. So here we are looking at the sight, the rear movable sight and the cylinder. And our job is going to be to line up the slit at the top of the nearby sight with the top side of the cylinder, and then go down and line up the bottom with the bottom. And sorry, I got it out of alignment there, but if we go over here, maybe it'll be clearer to illustrate. If I go down here and then slide on over, I've got them lined up on the bottom. If I go up here and then slide over this way, I've got them lined up on top. But I'm also going to show what it looks like if we zoom in and look through the sight at the cylinder. And let me point in the direction. There's our cylinder. And I'm wobbling a lot. There, that's better. Okay, now with some luck, it'll focus on the sky. And we can now move it around, and we can see how, if I can keep the camera lined up with the sight, we can see how you could move it back and forth, say to that little chasm in the clouds there, which keeps appearing and disappearing. There we go. Okay, and now we're going to go down to the bottom slit. Oh, there it is. Okay, and you now see that the bottom of the cylinder, if it will come into focus, is lined up, or can be made to line up with that same place in the clouds. And that is what we're going to be doing with the moon in the next shots. This is one of those chills up the spine moments. We are seeing what the moon looks like seen through Brahe's sights. This is something that nobody has seen for at least 300 years. Now, what you're seeing is an image of the moon, and that black square is the cylinder up in front. And you can see as I move the declination ring back and forth, we can reposition the moon in relation to that cylinder. And our aim is to get the top of the moon lined up with the top of the cylinder. So the moon is a little too high, or the instrument's a little too low. So we're going to have to adjust the sight, which we will do off camera. Okay, so now we've got the moon lined up pretty well. It's off to the left of the cylinder, and I'm going to move the armillary over until it just disappears. Now it's lined up with the top of the cylinder there. And perhaps that will be visible on the video. I'm going to slide it back out again, get it centered on the slit, and then back to where it's just disappearing. Now we're down at the other end, looking through the lower slit. That's what I mean. And we can see the entire moon. It is just grazing the bottom edge of the cylinder. And that's exactly the way we want it. So I think we've got ourselves a reading here, and I'm going to now look at the scale. We are now looking at the readout part of the sight. We've moved around the sight to the place where it is superimposed upon the Levy-Ben-Gerson diagonal scale. You can see the diagonal dots there in the little window between the two white pieces of plastic on the sight. The place where you actually take the reading is on the straight edge of the half or the crescent moon shape over on the right. Now, we're going to have to look pretty carefully at this. The engraved line that's more or less parallel to that to that readout straight edge is the 23-degree mark on the scale, and if you go to the right of that, either at the top or the bottom, you can see a kind of looks like a window set up. It's got three small windows on one side. If we're looking at the top, for example, three small windows, and then up above that a larger frame. The larger frame is half a degree wide, so we know that we're above 23.5 degrees. Each of those smaller windows, the smaller squares, is 10 arc minutes. So we're somewhere, we're not up to the end of the 10 arc minutes in after the 30-minute mark, but we're getting pretty close. Now we've got to count the dots, starting from the bottom there, and we get 1, 2, 3, 4, 5, 6, 7, 8, and you can just see the edge of the 9th dot peeking out there. So we're somewhere between 8 and 9 minutes, 23 degrees, 38 or 39 minutes. We could call it 38.5 minutes. Now, my setting of that sight was not really quite, it wouldn't justify reading it to the nearest minute, but it gives you an idea of how beautiful this scale is and how easy it is to read very small angles off of the scale. So we conclude the declination of the moon at that particular time, and if we were doing a real observation, we'd note the time, the date and the time, and it is 23 degrees, 38.5 minutes. So that is how the Brahean sights work with Levy-Ben-Gerson's scale. Every observation that we do with this instrument is going to be some variant of this particular procedure. You use the sight, you line it up on the object, you look through, and you line it up by looking at the slits and making sure that the object is caught around both sides of that cylinder. And then once you've got it centered as closely as you can, you then turn your light on the diagonal scale and read off the position. During the coming year, we're going to be trying to do things with this instrument. We have various projects. The simplest one would be try to see how accurately we can measure planetary and stellar positions. First of all, just getting the declinations. That's the easiest observation to do. How difficult will it be to measure the position of a star or planet along the equator, parallel to the equator? This requires coordination between two observers observing simultaneously, which was a particular challenge for Brahe and for his team. Can we emulate Brahe's observations of Mars at opposition to the Sun, which Kepler used to show the 8-minute error in the Ptolemy-Copernicus style theory? So there's exciting stuff coming up, and we'll try to keep the college community informed of this. Thank you all.